video on general chemistry. So today I'm going to discuss about the structure of atoms. That's my name and my Instagram. Please do subscribe my channels as well as you can have a look at my Instagram. So slowly those are the outcome what we are going to cover in this video. So we will start with the definitions and the calculations of the electrons, protons, neutron, atomic numbers, and etc. So guys, let's we talk about the behavior of the electrons. A few things that you need to know before we really go into the chapter. So the first thing is to know about the wavelength. Okay, so the graph, as from the graph you know that this is a simple wave graph. That wavelength is actually referred to the length between from this part to this part, or the length between this is what we call as the wavelength, or lambda. We refer to the lambda, or we can also have calculate the same wavelength, the lambda, from here to this distance. Also we will notice that it's going to be the same distance. So what I mean by a wavelength or lambda is the distance between the identical points on a successive wave. So it could be from this point to this point and this point to this point either. So amplitude over here is referred to the maximum distance at this particular regions. So the vertical distance from the midlines of the wave to a peak, or this one drop. So frequency is defined as the number of wave that pass through a particular point in 1 second. So from this if you guys, if you look at this wave properties, as you can see, the starting point of it will be here until to this moment. This is one complete cycle. So this is one cycle, and also we do have another cycle. This is another complete cycle for these wave properties. So actually guys, what I would like to show at this particular point, how to calculate the speed of using this thing is by lambda multiply with the frequency. So this is how we can calculate the speed of the wave. You might wondering why we need to calculate the speed of wave, because electron behave, the light behave in a wave properties. That's why we need to know the calculation of the speed of the light. So for information, this is the electromagnetic radiations. We have a different wavelength, as you can see over here. Different wavelength do correspond to different frequency. Definitely this can be calculated as shows from the previous slide. And each region of the wave actually do function in they have a different properties, and they have a different functions. As you can see, this region of the wave length is to do give the actually is X-ray regions, and we have a sun lamps. We have the region of the white this one gamma ray, X-ray, ultraviolet, and visible regions. We have this visible regions. We do have infrared, microwave, and radio wave. So different range. So, and also from here we notice that different wavelength actually correspond to a different color. This is what we call it the color spectrums. Sometimes we can relate this color to the color of the rainbow formations. Different wavelengths do give a different colors of it. So we can say the speed of the light is this 3.0 times 10 power of 8 meter per second. So all the electromagnetic radiations is, for information, lambda multiply with the velocity or the frequency, then it's do correspond to the speed of the light. Actually we do take this formula. Where do I get the formula? Is from the earlier slide, from here. Now the speed of a wave is actually correspond to the speed of the light, and this is the lambda, this is the lambda, and this is your frequency. So what is so important from this formula? We actually calculate the wavelengths of a different wavelengths of a different regions, let's say gamma ray, x-ray, by just know the frequency of the length, the lambda. So a simple calculations, remember a photon over here is actually referred to the light energy at the light, so has a frequency of this much. This is your frequency, and convert this frequency into a wavelength. Oh, so the information that's given, they give you the frequency and they ask you to calculate the lambda over here. Thus this frequency falls in the visible region. So guys, in order to answer this question, we need to couple these questions with the informations that given over here. As we know, the visible regions is, this is the visible regions, so we can recalculate it. So as shown at here, by substitute into the formula as given, a lambda times with the frequency equals to the light speed of light. So by rearrange the formula, then we get this, and we do know the speed of the light, that is a constant, and the lambda is given in the questions frequency. By substituting, yes, I do manage to calculate the lambda, the wavelengths of this photon. So by calculating this into a nanometer, you might wondering why we need to convert into a nanometer, because if we back to this region, do you notice or not, the wavelengths over here, it is in nanometer. That's why we will like to convert it back to the nanometer scale. So as over here, we managed to calculate the nanometer is a 5.0 times 10 power of 12 nanometer. Then by referring to the wavelength radiations, the wavelength, it falls between these regions. It falls between these regions. It is a nanometer of 5 nanometer, and it falls around here. So it is actually in the region of radio wave region. So slowly we go into a quantum theory. This is the simple definition of the quantum theory, Planck quantum theory. Those are the Planck constant theory, where quantum theory state that the energy in the dimension in the form of electromagnetic radiation. So that's the reason in the very early of the chapter I do introduce the electromagnetic radiation, the spectrums, and also the wavelength and everything, and can be emitted or absorbed in a discrete amount called quanta, a very small amount. Quantum is actually a small quantity of energy that can be emitted or absorbed in the form of electromagnetic radiation. Again, this is referred to the spectrums that we have labeled earlier. So this is the equation that we have learned. E equals to this one, hv, where the h is actually the Planck constants. It is in a joule over second. And of course we know this, we want to calculate the energy. And guys, if you still remember the frequency that we have calculated earlier, the v equals to c over lambda. So this part we can substitute over here. When we substitute, we can rearrange the energy of the energy of the electrons can be recalculated by substitute of this and get a hc over lambda. Again, it is a constant, h is a constant, c is the light speed of light, and lambda is actually referred to the wavelength. So by substituting, we can manage to calculate the energy of the quantum. So example, energy of calculate the energy in joules of a photon, the light with the wavelengths of this region. It is a infrared region. And a question number B, a photon with the wavelength of this X-ray region. So by substitute, the Planck constant is given. You know these constants. When you substitute lambda, as we know, the lambda is over here, and we change it to nano. Why? Because over here is meter. We don't want it in a nano scale, therefore we rearrange it in the form of a meter. So we want to standardize the unit. Once we have standardized, we get the amount of energy is this. So this photon have this amount of energy. It's a very simple to calculate. So this amount of energy, it is in a IR region. We can notice the amount of energy being released are extremely small. It is a power of 15, negative 15. So the next one you can have a try. It is more or less the same answer. So introductions of the hydrogen emissions Bohr theory. So guys, basically we have learned, we have go through that the photon, it have a different wavelength, and different wavelength it falls in a different regions. So as over here we can see, we try to duplicate this system in the form of like this. Let's say we have a discharge tube. Is a tube that we fill with a certain gases. Then we have a very high voltage to make it an anode and cathode, and we pass through the slit which is allowed us monochromatic light to bypass, and this monochromatic light will bypass and hit the prisms. And for information, when the light hit this prism, due to the difference in the angle over here, it will break according to like this. It will further be breaks, and it form a different color spectrum, light separated into the various components. So as you can see, the various components over here will be produced. We can presented it in a plate. We call it a photographic plate, and the line spectrum is over here is actually will be interpreted. When the electricity is passed through a discharge tube fills with the hydrogen gas. In this particular tubes are filled with the hydrogen gas. Why hydrogen? Simples, and it consists of only one electron. At a low pressure, a pink light is emitted. When the light passes through the prism, a line spectrum is obtained. So the whatever that passed through over here, the line spectrum over here is actually represents the energy gaps between in the hydrogen gas. So the energy supply is absorbed by electron. Of course, it's applied when we supply with some energy, the electron will absorb. This is a process what happens over here in this particular tube. So the energy electron of a hydrogen atoms cause them to be promoted from a ground state to a higher energy level. Remember, electron always will be at a stable state, which is the lower ground state, we call it. Then it will promote it because of the energy supply to an excited state. But nevertheless, when the electron jump to an excited state, it can't maintain the energy level for a very long time. So it will quickly fall back to the ground state. When it jumped to ground state to excited state, and it jump back to the ground state, and it will lose energy in the form of wavelength. This wavelength is what we will use it to calculate the photon. So it release, when it from excited state come back to the ground state, it release a photon, energy, a light. Transitions of the electron between two energy level produce a line in the hydrogen spectrum. So emission series obtained are classified according to the which level of electron drop to. If it is drop between the N1, the level of electron drop, so it have a different. When we are talking about this one, Lyman series is ultraviolet, Balmer is a visible regions, Paston infrared. So we will look at this in detail. So of course, now the atom gain energy. Okay, let's I put it in a picture to make it clearer. So this is where and in the initial, the electron will be located, and we are supplied with the energy to the atom. This will cause the electron jump from the ground state to the excited state. Excited state here stand for a higher energy orbital. From here, from ground state, it jumped to the excited state, but it can't maintain forever. It will come back to the ground state again. When it come back, it lose energy in the form of wavelengths. Then we can calculate the photons. So a specific energy value, the light is emitted as an electron move from one energy level to a lower energy level. So here is actually the excited state to a ground state. So this energy, this one can be calculated by using this formula according to Bohr model of atoms theories, where as you can know, this one is your principal quantum number. Guys, for your information, the principal quantum number here is actually referred to number of orbit. We have a first orbital, the second orbital, and third orbital, and so on. So now then we have this is a constant value that we will substitute, and we by substitute into this formula, we are allowed to calculate the energy level of the substance. So from the energy level, we actually can calculate we are actually in which region. We can know we are actually talking at which regions. So photon, again, the energy being released in the form of photon, light, wavelengths. So this can be calculated. So it is actually changes of delta E is a final minus with initials. So final is what over here, and this is your initials. By resubstitute over here, and initials is mean before it's the excited state, and also this one ground state. So we rearrange it, we substitute, we manage to get this. This is how we can calculate the delta E value. So this is where we must remember the final over here is where it come back to the ground state. Initial over here is actually stand for the excited state. So by substitute the amount and the energy, we substitute by substitute into this formula, we can calculate the energy gap between the orbital. So this is the amount. This is another examples. Okay, example, calculate this one. Guys, I know the energy of an electron when it's occupied a level equivalent to the quantum number of N3 and N4. So that it will happen at the energy is a N3. The energy of the photons emitted when 1 mole of electron drops from this fourth energy level to the third by substituting into this formula. This is your third, and this is your fourth. So they ask for energy, then we can minus. So we managed to calculate the third, fourth, and third, and the fourth and the third. So we substitute and we minus. This is the amount of energy between the third and the fourth orbital. Then we go to the next one. Noted. The negative sign that we calculate over here is just to indicate the energy being released when electron falls. So guys, over here we are actually referred to as exothermic reactions. So to calculate the amount of energy released by 1 mole of electrons, just multiply with the Avogadro constant. It is a 6.02 times 10 power 23. By multiplying this, we managed to calculate the amount of energy. So frequency and the wavelength, they are in the question, they do ask the frequency and the wavelength of this photon. So since guy we managed to know the energy by substitute into the earlier formula, which is the Planck constant value, the V equals to E over H, or just now we do it, E is equals to HV. So we substitute E is the energy gap, the energy. So you have calculate over here, you substitute, and this is a constant. Guys, please be aware of the unit. So you cancel it and go up, and finally the velocity frequency is, this is the value. So they ask us to calculate the frequency. Since we managed to calculate the frequency, we can reverse it, and it always frequency always have a positive signs, and we reverse it. We know lambda is equals to C over frequency. This is a formula that I have introduced in the earlier part of this video. So by substitute, I managed to calculate the value of the wavelength is 1875. So the photon release is region wavelength. So by looking at this region, we actually can determine the color of the photon or the light release accordingly. So guys, I will continue about the quantum number in my next slide. Stay tuned. Have a nice day.